So speaking of multi-core, it's one of the primary focuses of the presentation by the last presenter in this track on algorithms and implementations. So Tom Michiels from Synopsys is going to focus on pedestrian detection, which is an important function in a wide range of applications. A popular algorithm for pedestrian detection is HOG, the Histogram of Oriented Gradients. Several variants of the algorithm have been proposed. The complexity and diversity of these algorithms demands a programmable implementation, and he will compare and contrast the suitability of different embedded processor architectures to implement this algorithm with a focus on performance and power consumption. So, Tom?
Yeah, before I talk about pedestrian detection, let me say a few words about us and myself. So, Synopsys, you may know Synopsys primarily from being a EDA vendor selling EDA tools for designing ASICs like Design Compiler and VCS. We are a 1.7 billion company, and we're investing actually most of that money back into R&D. So out of the 8,400 people, more than 5,000 are like R&D engineers like myself. So what are we doing in embedded vision? Of course, everybody who would actually be interested in making ASICs for embedded vision may already be using Design Compiler and VCS. But we're actually also an IP provider. We're actually the second largest IP provider next to ARM. We're also having an FPGA-based prototyping system that we're actually also demonstrating upstairs. And finally, and that's what I'm working on, we're working on methodologies and tools for making application-specific processors. Processors that are very efficient in doing a very specific task. Pedestrian detection is one of the most popular embedded vision applications today. It has been a standard feature in luxury cars, but it's expected to be present in mid-size and compact cars in the coming years. And a big challenge, as was already described by many of the previous speakers, is that it's very difficult to actually implement this at a low cost and at a low power budget because it's a highly computationally intensive task. Most algorithms are actually that do pedestrian detection, like all popular ones are based on histogram of oriented gradients, and there's lots of variants on it, but for the purpose of this talk, we actually just used histogram of oriented gradients as is. Let me briefly explain to you how the algorithm works. So histogram of oriented gradients has the following 8 steps. After the grayscale conversion, it will take the input frame and it will scale it to different levels. It makes like a pyramid of different scale images. And the reason for doing that is that we want to detect pedestrians at different sizes. So you can see these are my daughters. They're not equal in size, and we don't want to make detectors for all different sizes. So we're going to scale the image first at different sizes and then use a fixed detection window that goes over all these layers in the pyramid. After that, we do Gaussian blur, and we compute the gradient for every pixel. So for every pixel in this pyramid, we will end up with a gradient. Gradient has an orientation and a magnitude somewhere. The next step is where the name histogram of oriented gradients comes from. So what we do then is we subdivide these scaled frames up in cells of 8 by 8 pixels. Actually, every pixel will be a gradient. And then we group these cells in blocks of 2 by 2 cells. So actually, every block is 16 by 16 pixels. And for every block, these blocks actually overlap. Like for every combination of 4 cells, we have 1 block. So for every block, we compute 4 histograms. The way we do that is we multiply the magnitudes of all these gradients with a bell-shaped Gauss curve in 2 dimensions. And then we distribute these magnitudes over 9 different bins according to the orientation that they get into. So for every block, we will end up with 4 histograms, each having 9 bins. That's the result of the next step, the most complicated one. After that, we take these 4 histograms, we normalize them You clip them and you normalize them again with L2 normalization. And then what you end up with is actually, for every block, you'll have these 4 times 9 values. And you're going to take this detection window of 64 by 128 pixels, and you slide it over your window. So for every detection window position, you will get roughly 3,000 of these histogram values. And those 3,000 histogram values you will actually classify by simply doing a dot product with a predefined set of coefficients. This set of coefficients is pre-computed by a large database of pedestrians and non-pedestrians. You end up then with a decision on whether a certain frame actually detects a pedestrian or does not detect a pedestrian. And of course, you need to group back all these detected signals from your pyramids, because the same pedestrian may actually be detected at multiple scales or maybe slightly translated one to the other. And you need to kind of bring that back. So that's the algorithm. Now, to give you some sense how computationally intense and difficult it is to do this, earlier today we had in the Xilinx presentation, I think they quantified the amount of computation for a 17-scale HOG as being 30 giga operations. Actually, what we're doing is the standard OpenCV algorithm, which has 28 scales in the pyramid. And if you run that on your desktop CPU, you actually can only compute 2 VGA frames per second on that. And that's, I don't know exactly how much your CPU would compute, but it will be roughly order of magnitude of 80 watts. A very good implementation that's doing it on VGA real time a few years ago on, okay, now it's not the state-of-the-art GPU anymore, but a few years ago it was still a state-of-the-art GPU. It was doing 20 frames per second, so that's actually kind of real time on VGA, the algorithm, on a GPU, but that one is actually, yeah, probably 1.5 billion gates and consumes 236 watt. And now recently, a few weeks ago, guys from Uncanny published a really nice video where they actually optimized the software. So they actually rewrote the algorithm in a very efficient way, and they got 7 frames, seven frames on a VGA frame on a Cortex A15. But that's really by optimizing the algorithm in a very impressive way. So what we did is we did not really optimize the algorithm. We took the algorithm as is and tried to make an architecture that would be able to do this in real time, the same performance as the high-end GPU, but do it at a dramatically lower gate count and performance. So the goals we set for ourselves for this exercise, and you can see the demo upstairs in the demo room, is to make a programmable architecture, fully programmable in C, C++, that can be programmed to do this, that fits in 500 kilogates and actually consumes less than 500 milliwatt. It turns out that as far as we have it now, we're going to be below 100 milliwatt. So that's kind of 3 orders of magnitude more efficient. And we do this by making processors that are highly specialized for this task. So I'll explain how we come to that. We haven't done like a tape out of the ASIC, of course, but we did an HAPS prototype that you can see upstairs. And the HAPS prototype is, of course, it's an FPGA-based prototype. It runs, of course, slower than the ASIC, and therefore it only produces 3.7. It runs at 60 megahertz, actually, and it produces only 3.5 frames per second. So how do we do this? In order to come to the very low power design, we need to make sure that we deal very efficiently with the memory. Actually, we try to avoid accessing the SDRAM as much as possible and use very small local memories close to the processor. So we choose to make a multi-core streaming processor with small local RAMs and 5 holes in between the cores. And we make everything fully programmable with a minimal risk architecture as a core for every processor, plus some special instructions on top of that. This is what the platform looks like. It has a DMA that streams in the video to an SDRAM controller and streams it out back. And there's 5 processors in there specialized for performing the different tasks of the HOG algorithm, each having their own local memory. This is the way we map the algorithm on there. So everything related to scaling and doing filtering, we do in the first processor. The histogram computation we do in the second. And to give you some sense again about the amount of computation you need to do, the first one, which is doing the scaling, blurring, and gradient computation, it really needs to do 6 cycles per pixel, do all that computation. That includes not only scaling, but also kind of retrieving the data and so on. The histogram computation, in the histogram computation, 4 histograms need to be computed, since we're running at 400 megahertz, in 400 cycles. And if you look at the dot multiplication, so the classifier needs to do more than 6 multiplications per cycle in order to kind of come to this performance goal for real time. So the data, the image itself, one of the key things for doing it low power is making sure that you don't try to move any data from one memory to the other that you don't really need. So we use the SDRAM essentially only to store the full frames and the scaled frames. All the intermediate data is kept in small 32 kilobytes or 16 kilobyte local memories close to the processors. So once the data is in the SDRAM, it's being processed by local cores, by the cores. Some of it is stored in the local memory, and the results of the computation are kind of forwarded to the next core. So we need to have some local memory because you need to have some context information. If you're applying a filter, just a 3x3 filter, you need to have at least these 3 lines of image data readily available for you to do the filter computation. And this applies to pretty much all the parts of the algorithm. You need to have some amount of line buffer locally to do the computation. So how did we come to this design? We started off by just taking an existing algorithm, and we used just OpenCV. We started refactoring that code, split it up in these 5 kernels. We did some profiling, and with this profiling, we found out roughly how much computation needed to be done. And we thought it would be possible to do it on these 5 cores. By doing this, I think we came very quickly to kind of a functional model, very conveniently, of the different ASIPs that we would later have to map the algorithm to. Then we took a compiler, just a compiler, and a basic RISC model that we have, and compiled these kernels on that RISC model. Of course, that's way too slow to actually execute at the performance that we need, but at least we were able to actually run these kernels on a very small embedded RISC processor. We took simulation models of these RISC processors and put them in a virtual platform that we were modeled in System C, together with some System C models of the DMA, the XI bus, and the SDRAM. And we could actually now simulate in System C the full Hoch algorithm, functionally completely correct. Obviously, it took quite long to simulate that. But since we could completely verify everything, including the communication over AXI and the FIFOs, we got it actually running first time right on the FPGA prototype. So we took the RTL of the RISC processors, and we could actually map the software, run on the FPGA, and it was working out of the box because we could validate it completely on the System C model. Now, on the FPGA prototype, which is running at 60 megahertz, we need to end up to 3.5 frames per second. And by doing it on simple RISC processors, obviously we were not getting there. Actually, we were by far not getting there. It takes about 1.5 minutes to process 1 frame on the FPGA prototype. But this was a base platform that was very easy to construct with existing blocks and was a good starting point for our specialized hardware. So what we did from there is actually profile the code on the different cores and try to understand where the bottlenecks are, and in a very smart way try to see how we can extend the architecture, maybe by adding register files, special dedicated registers for storing your histograms, for example, or by modifying the memory architecture, making the memory bus a little bit wider, or adding SIMD or a VRW slot, adding some vector instructions to it, or highly specialized instructions. And by doing so, we used processor designers to actually do this exploration, generate the hardware and the System C model, the compiler, and the software tools from that. We could very quickly come up with an ASIP design that we could then bring to the System C model, validate in the context of System C, take the generated hardware, put it on the FPGA, and see whether it actually was working as a whole. So that's how we incrementally kind of refined the model. So if you zoom into one example, for example, one processor which is doing the histogram computations is more or less the most complicated one of the system. What we did there is we added a vector slot next to the scalar instruction. So we added like 2 slot VLIW, just a scalar slot and a vector slot next to it. We added vector registers to it. we actually made the existing SRAM interface slightly larger, so both the scalar instructions as the vector instructions would be able to read from it, but the vector instructions can read it in one cycle. Then we actually we added also the FIFO interfaces. We added some very general purpose vector arithmetic instructions like vector multiply, vector addition and shifts, and so on. And then we added also a very highly specialized instruction for actually computing the histograms, because histogram computation is very difficult to do and even also really difficult to parallelize. It's very difficult to map it on a GPU. But if you do it in the real hardware, it's actually quite trivial. So we made a simple instruction that would take two vectors, one vector of angles, one vector of magnitudes, and distribute them directly into special purpose histogram registers. So by doing so, we increased, of course, the size of the RISC processors. We went from 27 kilogates to slightly under 100 kilogates. But we increased the performance by a factor of 200 by doing so. So we obviously had a much more power-efficient architecture by doing so. So these are preliminary results. We are still continuing the development, but you can actually see the current state of this design in the demo booth upstairs. So the prototype is running at 600 megahertz currently. So if you would actually implement it in an ASIC the way it is today, that would produce 23 frames per second at 400 megahertz. The 5 processors without AXI and local SRAM today, they fit in slightly over 328 kilogates, and the processors themselves without the SRAM consume today 72 milliwatt. Of course, you need to add the local SRAMs to that to be fair, but we haven't done complete gate-level synthesis of all that, but just from extrapolating from the data sheet, we think that will fit well under 50 milliwatts. So the full design will actually run at 100 milliwatt, which is dramatically lower than off-the-shelf processor IP. So yeah, please come and take a look at it at our processor booth. So to conclude, embedded vision applications require very complex, high computational algorithms to be implemented at very low power, but you need the programmability because of the complexity of it. Application-specific processors are actually a very good way to address the problem of combining the low power requirements with the programmability and the complexity and the high performance that is required for the algorithms. The performance gain that you get by actually tailoring your architecture to the problem is quite dramatic. And you can only do this not just by adding instructions, but also customizing your memory architecture, customizing the data flow, because lots of your power will actually go to your data, moving the data around in your design. And the key challenge, of course, is having a design methodology that allows you to kind of do this exploration in this architectural space. And that's what we're trying to help you with. So, yeah, that's it.